Okay, so for people who've done at least a slight bit of coordinate geometry, you might have had to learn the fact that if two slopes are perpendicular, their product equals -1. Or equivalently, m1 is perpendicular to m2, if and only if m1, m2 equals -1. Now, for the people who want to know why this is true, you've come to the right video. I'll be planning to do a lot more of these sort of proof style videos about different things. So definitely come to the right place here. So let's get started with the proof. So here we have two lines. I've tried to draw them as perpendicularly as I can. I think you did quite alright. So we have A and B. A positive slope, B negative slope. Obviously A is not that steep, B is quite steep. So that's sort of the gist with perpendicular lines. So how do we get to a situation where we have m1, m2 equals -1? Well, if I zoom in here really quick, just to add some detail in here, the angle that the line A makes with the horizontal, let's call this theta A. That is quite big, I'll make my pen slightly smaller. So this angle in here is theta A, let's say. And the angle it makes, or the angle B makes with the horizontal, this angle in here, is theta B. Now, if we go off the assumption that these lines are actually perpendicular, sorry about that, then we've sort of created a right angle triangle here. So actually, sort of to keep consistency, I'll add this in here. So this is a right angle. By complementary angles, this is right angled. And then of course, these two must be the same. So these are all right angles here. Okay, enough with the zoom. Okay, so we've had this situation here. So we can say that since we have a right angle triangle that looks a bit like this, with theta A here and theta B here. So we know that theta A plus theta B plus this angle here, 90, equals 180. Which implies theta A plus theta B is 90 degrees. So that's straightforward enough. The next thing we have to do might be something a few people have recognized by learning at this point. But if you have, actually no, I'll just draw it on its own. It's not a very straight, I'll try to make a straighter line. That'll do. So if we have this line here, L, let's say, it goes through 2 points. Let's say P1 and here is P2. And it makes an angle of, let's say, alpha with this horizontal axis. Now, if we sort of split this up into a right angle triangle, people who've done applied maths should be very well versed in doing this. So, there's one thing that we need to have clear, and that the slope of the line is the change in y over the change in x. You want to assume that's y2, take away y1, by the way x2, take away x1. This is just another way of representing it. Change in y over change in x. Now, if we treat this like a right angle triangle, this length here is a change in x, so this is, I'll actually write little delta x, change in y here, so little delta y. If we use tan here, so tan of alpha is opposite, so little delta y over the change in x, so little delta x, we can see that these two are equivalent. All I've actually done is capitalize the delta. So, since these two are equivalent, therefore, m equals tan alpha. So we've made a pretty neat discovery. So, what we can do here is we can say, let theta A, or well, tan theta A equals MA, and therefore tan theta B is M sub B. Now, with this, if we call this, or any one of the right angles here, let's just call it a new name, beta, we know that since beta must be 90 degrees, we should know that tan beta must be the same as tan of theta A plus theta B. So, this equivalence should be true if, by pure symmetry, that all of these are 90 degrees. Excuse me. So, what we can do now is expand this. Now, with trigonometric functions, it's not going to be tan A plus tan B plus some combination of tan theta A theta B. There is a special form of this with plenty of tutorials on YouTube, but this is equal to tan theta A minus tan theta B all over 1 plus tan theta A tan theta B. So, with this, we can now put this into the formula. Now, remember, beta's 90 degrees, so we can just say tan of 90 equals tan theta A minus tan theta B all over 1 plus tan theta A tan theta B. Now, you can sort of approach this in two different ways. So it could go off like this, but both of them will coincide with each other. So if we take a look at the graph of tan theta, so this is the y, this is theta, the graph of y equals tan theta looks something like this. So we're actually dealing with radians here. So if you remember parts of the unit circle, this is pi on 2. This is pi, 0, 3 pi on 2. So with tan theta, we have this sort of asymptote. Excuse me again. If we have the cosine component of an angle in the unit circle equal to 0. So we just get a straight vertical line. Now, this occurs a couple of times. Obviously, when you're going around the unit circle, it will obviously loop itself. So the first time this happens is at pi on 2. Then the next time it happens, well, we'll get to pi here again when it's flat. Then we get to 3 pi on 2 when it gets to a vertical line again. And here is horizontal line, so that would be at 2 pi. And then it just keeps going again. So tan theta has a weird period, has a period of pi radians, but we're just going to leave that out. So how can we use that information to help with this unpacking? Well, as theta approaches, we'll go pi on 2, as theta approaches pi on 2, tan theta approaches infinity. Now, I'll actually just write positive infinity just to make it slightly clearer, because it will reach negative infinity after one little flick, reaches negative infinity and comes back up. So we're just going to specify positive infinity, which is an approach of this point here. So, as this gets closer, this will have to tend to infinity as well. So, what we can say with these arguments, you can block this off with squarely brackets. If Microsoft Whiteboard can just be kind. Since my pen has disappeared. Where did my pen go? Why does my pen keep disappearing? What is this? Oh, whatever. So, this... God, this is going to annoy me. This should imply that tan A, or actually tan theta A, tan theta B, all over... Oh, that's so annoying. So, 1 plus tan theta A, tan theta B will also have to tend to infinity. So annoying with mouse. So, with this, if it's tending to infinity, then this bottom section will have to tend to 0. There's my pen back. So, I'll actually just make this slightly cleaner. 1 plus tan theta A, tan theta B tends to infinity. It looks worse, but whatever. Superhero logo. So, we can say that if this tends to infinity, then this implies that 1 plus tan theta A, tan theta B tends to 0. This can be shown because if you take the limit as, say, x tends to 0 of 1 over x, this tends to infinity if we're taking only the positives. Because if you have ever sort of played around with Desmos at all, you would realize the graph of 1 over x sort of looks a bit like this. So it kind of hits infinity from positive and negative. So if we're only concerning the positives, then yes, this is an equivalence. So we can simply rearrange this to say tan theta A, tan theta B tends to -1. Now, what have we recently learned tan theta A and tan theta B equal to? These are MA and MB. So we can say MA MB equals -1. Now, what does that entail? Well, we've assumed that... What's that down there? We've already assumed that these two lines are perpendicular. And we've shown that can only be the case if the product of their slopes equals -1. So, with that, we've proven it. QED.